On this lecture of a classical mechanics motion, lecture 1, we are going to talk about the very basic laws of motion starting from Aristotle. This is a very basic idea of describing the law of motion. That's the early time of describing motion from the old philosopher Aristotle. Law of motion. Aristotle boasted that the velocity of an object is proportional to the total applied force. He also stated that an object requires a constant external force to remain in motion. He's just arguing that the natural state of an object is rest. You know, if any object in a space, let's say we have a surface here, for any object in the universe, the natural state is rest. And you have to apply a constant and continued force to keep that object moving. It's mean eventually, you know, if you're just not going to apply force, then that body, that object, eventually going to be stopped. And to make anything move, you had to push it, you had to apply force to it, and the harder the push, the faster the object will move. Aristotle didn't actually wrote his law in form of equations and mathematical form, but his law would have looked like this in the modern language. That force as a vector force would equal to K times V. What K here could be as the resistance of an object of being moved. And the bigger the K, the more force you need to move the object. Well, this is Aristotle's law in a simple way, and he just came with some wrong conclusions because he didn't understand that friction is a force. Because if you apply the same experiment on an ice surface, then the same body, if you want to push it, once you apply force here, you will notice that body will keep moving without the need of constant external force to remain the body in motion. Actually, you will just notice it's actually hard to stop the object from getting moved if you just do the same experiment in an ice surface. Because here we have a friction force that keeps the body from continuous moving, which is on the opposite side, a friction force. Here the friction force is approximately 0. And that's why you will notice that it's hard to stop the body from getting moved. That's why the Aristotle law is not correct. But actually, Aristotle's law could be used as approximations, and especially when a friction force are strong, we can use the Aristotle law as an approximation. But also we have a better description of motion by this Isaac Newton. According to Newton's laws of motion, if you have an object in free space and with no force acting on it, with no external force acting on it, and that object is actually moving, and that's free space, it will keep moving forever if no force acting on it. It is what we call the Newton first law of motion. An object will stay at rest or continue to move in a straight line at a constant speed unless acting by a net external force. And this is the Newton's first law of motion and the law of inertia. And the word inertia here means, in Latin, the laziness. We can say, like, that we can say that the matter is lazy in that it does not change its motion unless forced to do so. And this is actually how, rocks and spaceships actually does not really require a continuous fuel, because you just need fuel at launching that spaceship or rovers. You just need fuel to change the direction, or when you want to do the acceleration or deceleration of these objects, and at launching. This is the first Newton law of motion. And the Newton laws of motion is the first law of motion is just a consequences of a Newton second law of motion. And the second law of motion, as we know, that's the force equal to the mass times the acceleration. Or we can say that the force equal to the mass times the rate of change of the velocity with respect to time. The key observations behind the new second law of motion can be summarized in the following experiment. If you're going to use a frictionless air track, that's a frictionless air track, and you have an object here, and you have a spring scale to measure the force. Let's imagine that the scale. And let's say the mass here, 1m, and the force is to just try to drag that object to measure the force. Let's say the force is here is F, and it will be accelerated as a value of a. Now, if you repeat the experiment, and at that time you just keep the same object, 1m, on the frictionless air track, with the same spring scale to measure the force, and here you just try to drag it with 2a, with 2 acceleration, with doubled acceleration. And you will notice that the force will also be doubled. And that's why he came with a conclusion that the acceleration is direct proportional with the force. This is the first conclusion. And he also repeat this experiment, but at this time he just duplicated the objects into another object attaching to each other. Now we have 2m, and dragging these 2m with the same force as F, and you will notice that if you keep the forces here constant force, and you will drag that two objects with a constant force as the case number 1 here, you will notice that the acceleration will be halved. When you double the mass at a constant force, then the acceleration will be halved. And that's why he came up with this conclusion that the acceleration is inverse proportional with mass. The acceleration equal to the force over mass, and force equal to mass times acceleration, the Newton's second law of motion. let's take an example applying the Newton's second law of motion. And also we can prove that the Newton law of inertia, the first law of motion, is just a special case of the Newton's second law of motion. Imagine that we have an object moving in free space with no force acting on it. Then the Newton second law of motion, or could be written as that form. That's mass times the rate of change of the velocity with respect to time. And since we said with no force acting on it, then F here would equal to 0. Hence, m times the rate of change of velocity with respect to time would equal to 0. And by the differential equation can be solved here simply. M times the integration from 0 to time, delta V over delta T times delta T. We are now just doing the integration of a derivative, would just give us this function, M Vt from 0 to T. That's equal to 0. M Vt minus M V0 equal to 0. And mv times vt equal to m v0. M could be cancelled out, and then vt equal to v0, which is here, is the velocity of that object at the initial time. And that's why the velocity at any time, that moving object will move, forever, because according to Newton's observation, then the velocity of that object at any time would equal to the velocity at the initial time when the force is 0, which is the same as Newton's first law of motion. And that's why the Newton's first law of motion is just a consequence of the second law of motion.